there was like an additional dialogue that I wasn't expecting.
Oh,
Oh no! Oh,
So
you
was I
screwed it
off
up,
by like a
what a
second?
letdown.
I know.
man.
Wah,
Wah,
wah.
wah. It was so close. So I found a new little gadget. I wonder if anybody noticed this, that you can say in advance that your live stream is going to happen on a certain time, and it was set to only let people know while the live event was actually happening, but you could actually
Mm.
modify it so it would set the live event to happen, to let people know a week beforehand. So I'd love to know if anybody who is here right now saw that notification. I turned it on this morning.
Is it supposed to come like via email? Because I'm pretty sure I'm subscribed to your email channel and I don't get anything.
uh, well, if you've clicked on the little notification bell for subscribing to the channel, then you'll get a notification on your whatever you normally use to consume media. um,
Yeah, I'm definitely, because I get the emails every week that say you've added a new episode of the Guide to Space.
Yeah. And
Uh,
then but this new thing should give you an additional, if you were looking at any of our videos this week, it'll say a little sliding comes up and goes that we're going to have a live event on Friday
I
at
don't
noon.
actually watch your videos.
I don't expect you to do so. That's
So that could be
probably
the-
best. All right, we'll give everyone 5 minutes. Arnstro loved Dr. Paul Metzutter's last podcast.
Was that the Kepler one? I think it was about Kepler and how he was a nutcase and not doing anything about what we think he was doing.
He was he a crazy person? Can you give us the 30-second version of this, the 1 minute versions?
He wasn't really a crazy person, but he was obsessed with numerology, and he was obsessed with finding fundamental patterns and harmonies in the motions of the planets that he could use for better, more accurate horoscopes.
And so he made the Copernican model work in order to really match the observations, just so he could get a better horoscope.
Yeah, he had an intuition that the Copernican model was better than the Platonic model because he thought, like, Jesus, the Son of God, is at the center of the Christian life, that the Son of the universe should be at the center. And so that was his big argument of why he thought the sun should be at the center. But he knew the math didn't work out, so he tried trying different fitting formula until he came upon the ellipse. And then once he had the ellipse, he could do all sorts of numerology to say deep things about the misery and famine and horrible things here on Earth because of our original sin.
That is so
Because
funny.
it wasn't a perfect circle.
Because it wasn't about circles. He was looking at the ratios in the maximum speed to minimum speed. And then he was comparing that to musical overtones. And then he was using that to say important things about like Jupiter or Mercury or especially the Earth.
Well, now part of that is cool. I'd love to see the whole like comparing the orbits to musical overtones and such. That'd be cool. I don't know that I would take it quite as far as to like talk about the human condition that way, but
yeah, one of his quotes that I'm going to butcher, but he said the ratio, the Earth itself has a ratio in as fast as the slowest speed of 16/15, which is the same ratio between fa and mi. Do, re, mi, fa. So and so he said, so fa and mi, that's famine and misery. So of course, the Earth is imperfect because it has these imperfect ratios and overtones.
That's awesome. I'm gonna say hi to a bunch of people. I'm gonna say hi to Adam McVeigh, Andy Smith, Bill Kay, Bob Harkins, Bob Moeller, Brian Yoko, Carolyn B, Colin Jones, Daniel McCool, Ilad Avron, Jill Sabrin, Hill Bierkog, Henrik Bo Anderson, Hugo Burnham, Jessica Feltz, John Hamilton, John Suffield, Julius Stenionis, Kenneth Lepre, K. Turbob, Leonard Lindstrom, Leonard Signitz, Lillian Brennan, Linda Sadek, Malcolm Bond, Max Decimus, Mokaba, Momo Dario, Nancy Graziano, Neil Hutchinson, Neil Giuri, Peter Grams, Peter Schultz, R. Instro, Rick Schwartz, Ronald McCoy, Arshawn 90044, S. Wolberg, Stephen Hawkins, T. Chris Wheeler, Tac Tang, Timothy Barnes, Tom C., Tom Van Scotter, Toxis, Vitek Ramba, William Vandebeek, Zach Cody, and Zap Van. Hey, if a person wants to get your podcast and listen to Kepler's Madness, what would they do?
They will go to askaspaceman.com, and if you listen to this, what I'm saying right now, within the next week or so, it will be the very latest episode.
Right on. Okay, I'm going to prepare us for this episode, a very special episode of the Weekly Space
Every
Hangout.
episode is special.
I know.
True.
That's the joke.
Oh.
That it's always a very special episode.
Oh, and here I thought you were saying I was special, but
No.
obviously not.
Don't get ahead of yourself.
Just like every
You guys
week,
are the best.
this is a very special episode of the Weekly Space Hangout.
With friends like you.
All right, here we go. Hello, everyone, and welcome to the Weekly Space Hangout for Friday, January 27th, 2017. I'm Fraser Cain, publisher of Universe Today. This week, we are going to be talking about exoplanets, and more exoplanets, as well as studying supernovae, making metallic hydrogen for the first time, what's the problem with Russian rockets, and testing for life on other planets. Joining us this week, we've got, I'm going to start with Paul Matt Sutter. Paul Matt Sutter, welcome.
Good place to start. How's it going?
There he is. Very well.
There I am.
We've got Morgan Renberg. Morgan.
I would never stoop so low as to talk about exoplanets.
No, it's not going to be you. And we've got Kimberly Cartier. Kimberly.
Hello.
And
I'm going to be talking about exoplanets.
you're the one who's going to be talking. Why are you not showing up when I talk to you? That's weird. There you are. Okay. So you're here to talk about exoplanets. So
All about exoplanets.
all about exoplanets. And actually, this week, you are not only one of our panelists, you are our very special guest. And this is a request, I think, that came from the WSH crew to dig more into your actual research as opposed to the news that you bring every week. We, of course, know you from such amazing pieces of news as Tabby Star and What's That Alien Megastructure? But you also have other research as well, and you are within striking distance of becoming a doctor.
I can see the finish line. It is in sight down the road. Yep. Not too far.
So then, for anyone who maybe doesn't know, this is of course my favorite question, which is like, who are you and what do you do?
My name is Kimberly Cartier. It's nice to meet all of you. I'm a grad student at Penn State University in the Department of Astronomy and Astrophysics. It's my 5th year as a grad student, and hopefully my final year as a grad student as well. I study exoplanets, and for the past couple of years, specifically the atmospheres of one particular exoplanet, and other related atmospheres and such. So that's what I...
Oh, I was just going to say, it's like... How do you study the atmospheres of planets orbiting other stars? That sounds hard.
It is very hard. You study them very carefully, and you endeavor not to claim too much with the limited observations you have. So the atmosphere that we were studying, and really the types of atmospheres you're mostly limited to, are the atmospheres of hot Jupiter exoplanets. Ones that orbit their stars within a couple days orbital period. So the one I've been studying is called WASP 103, or WASP 103b, and it orbits in only 22 days. It is what we call an ultra short period exoplanet, and it has, I think, one of the top 5 shortest orbital periods of exoplanets, and certainly one of the hottest atmospheres on record.
Right, and these first planets that were discovered back in the as planets were first discovered, this class of hot Jupiters were picked up early on.
Yeah, things like 51 Peg and other exoplanets like that. They are relatively easy to find, and they're very numerous. We've learned, and because they orbit so close to their stars, they're incredibly hot, and they have really deep transit signals. And if you're going to study the atmosphere of a planet, you need to use a transit or an eclipse of the planet itself to get the atmosphere. So that's what we were doing. We used Hubble Space Telescope to do this, actually. And Hubble is in no way, it was never designed to do the types of observations that myself and other exoplanet people have forced it into doing.
Poor Hubble.
Poor Hubble. We're sort of pushing it to its limits, to the very, very limits of what this detector can do. And Hubble can get maybe 24 of the thousands of exoplanets that we know of. Hubble can observe maybe 24 of them. That's sort of the cutting edge of where we are right now.
Right, and I mean, Hubble was never intended. I mean, Hubble can do some infrared, it can do some visible light, it can do some ultraviolet, but it is not intended as a exoplanet atmosphere observing platform. Are there better tools out there than Hubble for this job?
Spitzer can do a better job, not maybe a better job, an equal job in a different part of the wavelength spectrum for exoplanets, because Spitzer can go farther into the infrared, where most of the starlight tends to drop off, but the heat from the exoplanet starts to rise. And if you want to observe the light coming directly from the exoplanet, the planetary emission itself, you really need to look in the infrared part. And like you said, Hubble can only go to the very near infrared, like out to 2 microns. But really you need to go more towards 4 or 5 microns so you get more of the planetary emission and less of the stellar emission, to try and get a spectrum of the planet's atmosphere, to look for the temperature, what kind of molecular species are in the atmosphere, try and get the temperature of the planet's atmosphere at different heights. So building up that temperature profile that'll tell us what kind of chemistry and physics is happening in the actual atmosphere.
So let's talk about WASP 103b. Is it a terrible, terrible place?
Well, it's a terrible place for us to live, that's for sure. It is about half as hot as the sun, so that's no good for us. But it's great for the observations themselves. And as it turned out, and we had no idea ahead of time, but as it turns out, the atmosphere of WASP 103 is actually pretty strange. It does not conform to what we think it should be. So our Hubble observations, we expected with this atmosphere that it would look like a typical stellar atmosphere or a brown dwarf atmosphere, where towards the interior of the planet it would be very hot, and then the atmosphere cools off as you get closer and closer to space at the top of the atmosphere, a standard decreasing temperature profile. And then when we actually looked at the emission from this atmosphere, it didn't look like that at all. In the region we were looking, the temperature almost stayed the same at all the different heights that we were looking at. And that meant that there's something, the atmosphere is hotter than it should have been, essentially, which means there's something going on that makes the atmosphere warmer than it should be. And
not just being super close to its star.
It's not just that.
It's hotter than it would be.
It's hotter than it would be even that close. So with exoplanets, we've never really seen this. There's maybe 2 other planets we've seen something similar to this. This is one of 3, where there's some sort of weird warming effect going on. But what's interesting is that this is a phenomenon we see all the time in our own solar system. Earth does this, Jupiter, Saturn, Uranus, Neptune do this, Titan does this. Nearly every single atmosphere in our solar system has what we call a thermal inversion layer, where as you go higher and higher, instead of getting cooler, the atmosphere actually gets warmer for a time before then getting cooler as it goes. And for us on Earth, it's because of our ozone layer. It's because the ozone heats a little bit of that air just above the ozone layer, which is nice for us. It protects us from all these harmful radiations and such. And this is a feature that we really, really want to find on another planet, because for us on Earth, the fact that the ozone layer exists is very helpful for us and for life on Earth. We want to find that somewhere else. And there's maybe 3, including the one that I was studying, that maybe have this feature.
Is the planet tidally locked to its parent star?
We think so. It's close enough. It only orbits at 3 stellar radii away from its host star. It's very close, so it's probably tidally locked. But we've never actually gotten a full measurement of the atmosphere for the whole orbit.
If we could orbit it, like we've seen these beautiful images coming back from Juno of Jupiter, if you could orbit this planet in the sort of the way that you would with Juno, what would we see?
Oh, that's a very good question. We'd probably see a lot of hazes and a lot of clouds in the upper atmosphere to make probably what's causing a lot of this warming effect in the atmosphere. We have no idea if we'd see anything like the band structures that we see on Jupiter, because we don't know what sorts of molecules are in the atmosphere to be causing any of this. We don't know how the atmosphere is mixing top to bottom or day side to night side. There's still so many things that are unknown about this planet. But we think that there's probably an upper atmosphere haze, sort of like we see on Titan or Pluto, because there's some weird scattering that's happening more in the optical part of the spectrum, which looks at more of the upper atmosphere. There's way too much optical emission. So we think that there's some sort of scattering effect happening way at the top of the atmosphere, but we're still working on that.
Now, you say that Hubble is only really able to give us direct images of the atmospheres of a few planets. There's a new observatory that's going to be launched in the next couple of years, the James Webb.
I've heard of that.
You've heard of this, yeah. How much of a difference is James Webb going to be for the work that you do over Hubble and even some of the other instruments out there?
So, I mean, just like Hubble, James Webb wasn't really designed for the purpose of exoplanets, but it's going to be such a perfect instrument to do exoplanet atmospheres, primarily because it is looking more in the infrared, and it's looking at very high resolution across a very wide swath of the infrared spectrum, and that's really what you need for exoplanet atmospheres. So James Webb is going to really, really help, I hope. But I really hope.
Yeah.
At the same time, like all the stuff we're doing now with Hubble for the handful of exoplanets we can, we're developing all the techniques and the software and all the analysis methods and the models of planets as much as we can. So when we get James Webb, when we get those observations, we'll be able to hit the ground running with them.
Right. And I think, are you observing this planet because you're fascinated by this kind and class of planet, or you're observing this planet because these are the ones you can get the data? If you sort of had your dream, what kinds of atmospheres would you be studying?
My heart always lies with habitable zone planets. So me personally, if I could observe an atmosphere of any planet, I'd pick a habitable zone one. But at the same time, hot Jupiter atmospheres are so fascinating because they're so different. We don't see anything like that at all in our solar system. We had no idea these planets even existed 20 years ago. And just they behave so differently that it's a fascinating thing to see. And it sort of tests the extremes of what we understand about our atmospheres and so-called standard colder atmospheres. It's testing our best guesses.
Right. Well, let's go back to the habitable atmospheres for a second there. So if you did have, like I will wave my fairy wand and you'll get a observatory capable of detecting the atmospheres of a planet in the habitable zone, what would you be looking for there?
Ooh, I would be looking for thermal inversion, something to get rid of all of the harmful UV and X-ray and gamma ray light, things that wouldn't be conducive towards life. I'd be looking.
So in other words, if you could, I'm sorry to interrupt, but if you could observe the Earth from afar and you could see that temperature inversion that's going on, you would know that there's some kind of protective ozone layer that's here that's helping to contribute to that. That's interesting. Okay, I didn't know that.
Yeah, so that like I said, it's sort of like the Holy Grail. No, maybe not the Holy Grail, but it's more like the big white whale that we're looking for.
Right.
We want to know that it happens outside of our solar system. So I'd look for that. I would look for a huge water absorption feature in the atmosphere. So not only does it need to be protected, but we probably think it needs to have water. And water shows up very clearly in the spectra of lots of hot Jupiter exoplanets even. We know that water exists elsewhere and we can find it. And if I were truly wishing, if I could get like anything I want, I want I would want to see the red edge of chlorophyll.
What
So,
would that tell you?
so if you look at the spectrum of chlorophyll, which makes up most of our plant life, you see a very steep cutoff where just the amount of light sharply drops off right around sort of like the red wavelengths. So like visible red moving into infrared, there's just a really sharp drop where that the chlorophyll has. So if we found that somewhere else, that'd be that'd be my holy grail. I would love to see that evidence of plant life on other planets. Highly unlikely.
But that's of course wishes, assuming that life will evolve in a similar way, and that you're going to have chlorophyll, that same process.
Assuming,
but aren't there other gases? I mean, we're studying the methane in the atmosphere of Mars and trying to use that to necessarily tie it to life, right?
The thing with methane and CO2 is that there are ways to make them without life being present. And we don't yet understand sort of how much, where that differentiation would be if we detected methane and CO2, which we have in other atmospheres. What would be the probability that something organic caused it or something inorganic caused it? Maybe it's from a geologic process instead, which doesn't necessarily mean that life's there at all. So if we're trying to find true evidence for life on another planet, we need to go for the positive definite molecules and signatures in these spectra, things that have no other possible explanation.
What about some of the other tools that have been proposed, like using some kind of coronagraph to be able to view the atmosphere of other worlds? Are there a lot of stuff sort of in the works that are going to take your observations to the next level?
Things like GPI would probably help, which I think we're going to talk a bit more later. But as much information as we can get about the atmosphere from the emitted light, from the transmitted light, so the starlight that's passing through the atmosphere itself, or the reflected light as well, any sort of information we can get will help us pin down what the composition and temperature and dynamics of these atmospheres are. So coronagraphs definitely will help. Anything with transits will help. Any really sensitive detectors, things like VLT and such, will really help as well.
And we've talked about this a bit in the last few weeks, of course, just about, for the longest time, we thought it was going to be really space-based observatories that were going to be carrying the load. But now it really looks like a lot of the ground-based observatories are filling in the pieces as well. It's sort of a revolution in both fronts.
Yeah, the ground-based telescopes are definitely helping a lot. But the issue with the ground-based telescopes is that they have to look through our atmosphere. And for the atmospheres of other planets where we want infrared light, our atmosphere gives off a lot of infrared light as well. So ground-based telescopes in the infrared, it's a lot more challenging to deal with. And there are a lot fewer clear areas to look in.
So I got a couple of questions from some of the people watching right now. One from Tom C. How can the planet orbit so close and so fast to the star without being torn apart?
Well, the planet itself is also very massive. So in terms of WASP 103, it's about 1.5 times the mass of Jupiter, which means it has a lot of its own gravity to hold it together. That being said, it does fill about 60% of its Roche lobe, which means that it's also slightly aspherical. It's being tugged a little bit by the star. So it's not a perfect sphere, but it still has enough to keep it holding together.
So it's almost like
it's a little bit ovular,
teardrop shaped a bit. That it's
a little bit
without a point, but the side that's facing the sun is being kind of pulled towards it.
Almost a little pear shaped.
That's crazy.
Yeah.
Yeah, it'll be amazing to see it up close. And from Max Decimus, what's the main composition of WASP 103b?
It's still going to be mostly hydrogen and helium, as most gas giants and stars and brown dwarfs are. But it's really the trace elements, all the little metals and the molecules and such in the atmosphere that really make the difference as to what we'll actually see.
Right. Very cool. Now, we've mentioned sort of leading up to this, you are sort of in the final stages of becoming a doctor.
Yeah.
So where
Man,
are you?
isn't that a scary word?
Yeah. Dr. Cartier. What is the
Yeah.
sort of, where are you now, and how many more hoops must be jumped?
I still got lots of hoops to jump, less than I did a few years ago. I will hopefully be defending my dissertation sometime mid-April. The exact date is still to be determined. I have to get all 6 of my committee members in the same place at the same time
Right.
for like 3 hours
Herding cats.
in the middle of a semester.
Yeah.
So we'll see. But yeah, middle of April will be a defense, and then I have to submit the thesis, all however many 100 pages of it there is, and then I don't have to walk, but I'm going to walk down the graduation aisle with the cap and the gown and the funny robe and such. So hope this whole process will be finished by August, less than a year.
That's fantastic. Ed Walczak says, Dr. Cartier, I presume.
I'm, crossing my fingers. Don't jinx it, guys, you know? Don't jinx it.
Well,
there's still so many things that could go wrong.
And so if people want to follow and watch your journey, what is the best way for them to see what you're up to next?
Yeah, so as always, people can follow me on Twitter at AstroKimCartier and my website, KimberlyCartier.org. And actually on my blog as well, which is found on my website, I've started a blog series chronicling the next couple months on my road to the PhD, all the different hoops and what it's like with your boots on the ground. What is it really like to approach the finish line of a PhD? So intermittently, I'll be updating that. So
that's really cool. I think that's great for a lot of people. Where you've gotten to in your career is a very kind of theoretical thing. You see the doctor, the PhD at the end, but you don't actually see all of the individual small steps, the decisions that you have to make to get there. So I think that's a really valuable service that you're providing people.
Well, I hope that people find it valuable. It's part journal, part catharsis, and part informational, I think.
Yeah, fantastic. So. Well, thanks for joining us on the Weekly Space Hangout this week. I hope now you'll join us.
People. Yes,
and we will. You'll put on your regular contributor role, and we've got a couple of stories, including what I think is the most phenomenal video I've seen.
It definitely should be winning an award.
Yeah.
It should be nominated for whatever that movie award is.
Whatever that is. So we'll get to that. Stick around. We're going to get to what I promise is going to be the most mind-bending video I think that many of us have ever seen. So let's move on to the rest of the team now. I'm going to start at random, as I did before, with Morgan Renberg. Turns out we made metallic hydrogen.
Yeah, as cool as Kimberly's video is, I think this is actually the most remarkable story that we'll talk about this week, because the journey to try to make metallic hydrogen is one that has been going on for more than 80 years now. And just sort of as background, any element can be a gas or a liquid or a solid, depending on the temperature and pressure that you find that in. So some very light thing like hydrogen, here on Earth, we tend to see it only in the form of a gas. It's in our atmosphere. In fact, it's so light, it floats away from our planet and gets lost to space. If you cool it down, you can turn that into a liquid. And that was one of the major breakthroughs of the early 20th century, was the ability to turn hydrogen, helium, these other light gases into liquids. We now use these liquids for all sorts of industrial applications. But if you continue to cool it down and compress it down, in theory, you can turn anything into a solid. And we figured this out back in 1935 when we were tinkering around with quantum mechanics to try to understand how atoms and molecules work. And when they first realized that you could turn hydrogen into a metal, they thought that it would take a large amount of pressure to do that. Amount of pressure that we'd say is about 25 gigapascals. Gigapascals, a unit for pressure, it means billions of pascals. And 1 gigapascal is about 10,000 times the pressure exerted by our atmosphere. So in order to take this metallic hydrogen or this hydrogen and make it a metal, you'd have to put 250,000 times the atmosphere's pressure onto it. And obviously that would be a very challenging thing to do. So it's no surprise that we found no metallic hydrogen in nature on Earth. And so we started trying to do this, and you try and wouldn't get there, and try and you wouldn't get there, and try and you wouldn't get there. You get to 25 gigapascals and nothing would happen. You get to 50 gigapascals and nothing would happen. And that's because we realized in the 21st century that we were sort of missing some of the physics going on in understanding what turns hydrogen from a liquid to a metal. And not, instead of 25 gigapascals, we actually needed more like 400 gigapascals. So that's about 4 million times the pressure of the atmosphere. And that's just something that mechanically we've only begun to be able to create. And so a pair of researchers have been working with basically a vise that you put liquid hydrogen into, and you just crush it down and put more and more pressure. And they got it up to 300 gigapascals, 350 gigapascals, 400 gigapascals, and still nothing happened. And they just kept going more and more and more, and still nothing was happening. And they were trying to figure out, well, what the heck is going on? And it turned out that the pressure you needed to exert in order to metallicize this hydrogen was so great that it was literally breaking the diamond that they were using at sort of the blades of their vise. And so the diamond had little imperfections in it, and as the pressure increased, those imperfections would start to deform, and the diamond would shatter, and you weren't able to generate enough pressure. So they fixed that. They ground the diamond down to be extremely smooth, no imperfections. Then they found that as you increase the pressure even further, it would start to actually force the hydrogen molecules into the diamond itself. So you take this diamond, the hardest substance that we know, you're actually forcing hydrogen into it faster than you were compressing the hydrogen. It would break the diamond again. And so they had to put in some more material around it that was designed to absorb hydrogen before the diamond would, so that you could increase the pressure without breaking your diamond. So eventually they get this liquid hydrogen up to a pressure somewhere between 465 and 495 gigapascals. So that's almost 5 million times the pressure of Earth's atmosphere. And then suddenly it just turned shiny. And shininess is one of the sort of main markers that something is a metal, a solid. And one of the most interesting things that they found is, so I said at the beginning that they put this supercooled hydrogen into this press and crunched it down, and eventually they made a metal. But once it became a metal, they were able to raise the temperature, and it still stayed a metal, higher than you would expect to find a temperature that would allow for solid hydrogen. And so this means that there could be all sorts of applications for metallic hydrogen that work at these higher temperatures that wouldn't work at the temperatures you needed to make actual metallic hydrogen from the start. And so that's like all of the useful, interesting physics aspects of this. But why am I talking about this on a space show? And that's because we think that metallic hydrogen does exist in nature. We think it exists near the core of giant planets like Jupiter and Saturn. And this has been a major obstacle for us to understand the formation and evolution of giant planets. Because typically how we do this is we look at a planet, we make some measurements from the outside, and then we compare those against physical models and laboratory experiments of the stuff we think is inside that planet. And we sort of predict how it will behave as you change the conditions. But because we had never made metallic hydrogen, and because our theory of how metallic hydrogen should be made didn't seem to be working, we were never able to sort of predict what the inside of a gas giant planet would look like. And now that we have the beginnings of laboratory experiments with this substance, we're going to be able to put better constraints on, well, what are the properties of metallic hydrogen? For example, these researchers have already found that it was 15 times denser than liquid hydrogen. And so that tells you, if you have a certain mass of hydrogen, how much space is it going to take up? And since we know the size of the planet Jupiter, and we know the mass of the planet Jupiter, and we know things like the density of ice and the density of nitrogen, and the density of helium, and all of those things, we can, now that we know the density of metallic hydrogen, we can start to estimate, well, how much metallic hydrogen is actually inside of a planet like Jupiter. And that's really, really important for understanding the boundary between when a planet becomes, for example, like a brown dwarf, when these gas giants sort of reach their equilibrium size. So Jupiter is actually still shrinking. Its gravity is more powerful than the forces pushing the gas in it down. And so we don't know exactly how that process ends. And by understanding something like stuff at the center, that'll be a real big opportunity for a breakthrough.
And I mean, it's always funny to me when people think, like, you know, if you jumped into Jupiter and you fell down through the clouds, you would eventually land on, you know, on this, you know, how can you walk around in a gas planet? Is there some solid surface down below? No, hydrogen is under such heat and pressure that it's formed into a metal strong enough to break diamonds. Like it is not a place that you would want to visit. Is this the final stage for a planet like Jupiter before it actually does turn into a star? Like we know with a place like the sun, the temperature is whatever, 25 million Kelvin. You've got fusion. But in the case of, you know, Jupiter, I think what's the temperature? 25,000 Kelvin or something. So there's this sort of difference, right?
So a planet the size of Jupiter will never become a star. It will never even become a brown dwarf. It's just not exerting enough pressure at its center to push those hydrogen atoms basically into each other, which starts the fusion process. But if we were, for example, to start throwing more and more material, if we had 50 Jupiters and we could just start throwing Jupiters together, eventually we would add up enough material that it would start to undergo this fusion process and become a star. And we don't have the possibility for that in our solar system. Right. But when we look out at other solar systems in the galaxy, we see all sorts of objects that seem to be very close to straddling the border between star and planet.
But that metallic hydrogen is sort of the final step until you get to fusion. I wonder if there's some in between where there's like different forms of metallic hydrogen, or is it always just the same? It's the same structure, because metals are, you know, have this kind of crystalline structure to them, and so will it just be, or are there other forms of metallic hydrogen?
We just don't know right now, and the fact that making this in the lab allows us to refine the theory, because now we have something actual physical to predict against, and they'll be able to improve the theories such that they match the observations, and then we'll see, well, what else do those theories predict? Yeah. Before we had these theories, but we had basically no idea whether or not they were right, and that made it even more uncertain to try to make, you know, farther predictions out of that, and this really opens up the door for all of that.
All right, well, everybody hold in their brains this monumental accomplishment of science, creating metallic hydrogen for the first time, because we're then going to compare the emotions you're going to feel in a second when we show this video. But before that, as a palate cleanser, first to break, we're going to talk to Dr. Paul Metzetter, and we're going to be talking about using AI to study supernovae.
Yeah, there's all sorts of interesting, very challenging, very difficult problems in astronomy, especially when it comes to very large data sets, like when we're trying to study supernova to measure distances and get a handle on the Hubble and the expansion rate of the universe. And especially when we're trying to do this very, very, very precisely, where we're trying to get very accurate, say, distant measurements. These very accurate distant measurements rely on understanding very, very well the actual true brightness of the objects we're studying. And so there's lots of approaches to these kinds of problems in general, and one kind of approach that's gaining a lot of momentum in the astronomical community is using neural nets, which are computer programs that mimic how brains naturally learn and problem solve, where you have some data set where you know the answer, and you apply these algorithms to essentially train the algorithms on these data sets where you know the answer, so that they can pick out little subtle differences, little differences that a normal algorithm that's just trying to brute force stuff isn't going to be able to pick out. Then once you're satisfied that it's trained on that data set, which can usually take a pretty long time, then you unleash the full algorithm on the full data set where you don't know the answer, and it can pick out features, pick out signals that other algorithms may not be able to pick out, and you can use that to get very accurate and very precise measurements that you then feed into the further analysis. And so there's a few examples of using this, especially the article I read of how this is used in the context of supernova. One is in trying to distinguish type 1a supernova. This is when a companion accretes material onto a white dwarf and the white dwarf blows up. These are really, really great standardizable candles that we can use for cosmology distant measurements versus core collapse or type 2 supernova, which sometimes they look very, very similar. And we have a hard time separating them. We don't want any of the type 2s, the core collapse, in our beautiful, pristine sample of type 1 supernova, because then that ends up screwing up our measurements. So we want to be able to cleanly separate.
Right. And then people say that like dark energy might not exist.
And then we got problems, but I don't want to go down that
I know
road.
you don't want to go down.
Get into another rant.
No. Keep one rant per week.
That's the limit. That's what I promised you. And there's also, let's say we are looking at these pure, pristine type 1a supernova. Well, there is some natural variability in the properties of the stars and the white dwarfs that are creating these type 1 supernova. And that means they have a little bit variation in their brightness. And when we're trying to do very precise cosmology, we need to understand these very, very tiny little differences so we can account for them in our models, and we can get very accurate distant measurements. And so again, we can use this emerging technology of neural nets or neural networks to pull out those tiny little pieces of information.
Right. And I guess I was reading a newspaper report just today, I think, that AI or these kinds of neural networks are getting really good at doing things like helping doctors diagnose skin cancer. You feed the neural net a whole bunch of images of what skin cancer, an actual case of skin cancer is, but then also things that aren't skin cancer, and you teach it both, and then after a while it starts to learn and pick up its own signs that you as the computer programmer don't even necessarily know why it's doing this. So it's the same situation. You're feeding it a whole bunch of type 1a supernova data and feeding it a bunch of type 2 and different structures and saying, learn to spot the difference and learn to help us in our observations.
Right, exactly. It's taking those known data sets where we know the answer and where the differences are obvious, programming that in, say, hey, here's how these two populations are different. Find the best way to separate those two populations based on anything you can find, obvious stuff or non-obvious stuff, non-obvious differences, then go into the real data set, separate those out, give us some clean populations. So basically we're making Skynet, but instead of destroying and enslaving humanity, we're learning about the distances in the universe.
Awesome. All right, Kimberly, it's time for us to really blow everybody's mind here. We're going to show them that video.
My favorite movie of 2017.
Exactly. Now, do you want to set this up for us? What are we going to be looking at here?
We're going to be looking at the light reflected off of 4 Jupiter planets in a distant solar system.
All right.
Hundreds of years ago.
Okay, I'm going to bring up the
Dramatic.
browser now. You can't see it, but you're going to sort of go along with your imagination now. So I hope everybody can see this. All right, you ready for this? Ready for this? There's like a yellow
So
star
ready
in
for
the
this.
middle. There's like a black circle around it. There's a bunch of blobs of light. All right, here we go. Check this out.
Take a look. Take a look. Look, they're going.
Yeah,
Look at them go.
the
Look at those planets.
those are planets
They move.
orbiting another star.
They are. We're looking at the actual motion of these planets observed from 2009 up until the end of last year. 7 years of motion of these planets.
That's
all
seven
taken.
7 years of motion of these planets going around, and
It's phenomenal.
so how close are these planets compared to, in terms of our own solar system?
Actually,
Well, I'm just trying to think. Like Saturn
the
takes,
inner
like-
one orbit. The inner one orbits in 40 years. The inner one orbits in 40 years.
yeah.
So somewhere,
So I'm trying to think. Like Saturn is like what, 28 years?
yeah.
So
So
it's
somewhere Uranus like orbit
Right.
on the inner one, and then the outer one is like 400 years or something.
all right.
Yeah. What's really cool is that the 4 planets are in the same resonance as the Galilean moons of Jupiter. It's a 1 to 2 to 4 resonance. So cool.
And the mind-bending part here as well is that you look at the date go up, right? 2009 all the way up to 2017. So
Yeah.
so the fact that they were observing this for so long and
It's so cool.
I got nothing. That's really cool. So is this
It's just like
especially
nice.
hard? Was there some special technique to be able to do this? I mean, I don't recall I've seen occasional pictures, but I don't recall seeing a lot of this done before in the past. Is there something special that they did with this?
I don't know. I think it was just
Yeah, they took a
they
lot.
took a lot of images. They took a lot of
It's-
pictures with Keck over many, many years and put it together in sort of like a time lapse.
Yeah.
Very similar to what was done last year, I think, with GPI on Beta Pic.
Amazing.
It's just so cool that we're at the place where we've been looking at these systems long enough with this direct imaging technique that we can actually observe the passage of time in another solar system.
And so I think that if
Right.
you could look at this, and I'll show this one more time here, just to show people.
Sorry, I'm geeking out a little bit.
No, it's fine. It's fine. So am I, right? If you could, like a coronagraph, so that black
Right.
circle that's in the middle, that's the coronagraph blocking the light from Keck of the star and the surrounding environment, so that we can see these
Yep.
dimmer planets that are going around it.
Oh yeah, and these aren't young, just formed planets. I mean, they're, like I said, the inner one has a 40-year orbit. It's not a super hot planet like a hot Jupiter or anything like that. This is the actual light reflecting off the atmosphere, and these things are so faint.
Yeah.
This coronagraph is so good.
Yeah, and the other part, of course, is that the being able to see these worlds, you couldn't detect them with either the Doppler method or with the
No.
transit method, because they are face on.
Yeah.
If you go to, sorry, people are asking where to get the link. If you go to astrobiology.nasa.gov, it should just be /news. So
Here,
but
I'll
it should
also
be just
post
on,
one in
on
the
NASA.
chat.
Yeah.
Let me copy paste this link into the chat there.
Yeah. So
But yeah, this is a whole different type of system that we would never have picked up on with any other method that we have.
yeah, and so you can imagine a whole other method of observing planets is you just look at all these stars and you just take pictures of them over time very carefully using a chronograph to block, and then not only do you see the stars that happen to be lined up, but you see them all. It's so, again, I don't want to make metallic hydrogen and directly
I think
observing
you've
7
just
years of
described,
exoplanets.
I think you've just described like half a dozen exoplanet missions that NASA said no to over
Yeah.
the past decade.
Yeah, like the terrestrial planet finder, things like that.
Mhm.
Yeah, absolutely.
Yeah.
NASA,
It'd be
please
great.
say yes. If
It'd be
NASA's
great.
watching right now, say yes to an exoplanet observing mission. That would be super.
Please? Well, that's nicely.
All right. All right, let's move on to Morgan again. And we're going to talk about why, what's the matter with the Russian rockets?
Yeah, I was here a week ago talking about how NASA was planning to buy additional rides to the International Space Station aboard the Russian Soyuz system. And this week we find out that I won't say that might be in jeopardy, but that there are issues with the Russian systems that hadn't been previously disclosed. And so over the last year, there have been some high-profile failures of both the light and heavy launch systems used by Russia. Their Proton system for sending up like spacecraft and satellites and things like that, and the Soyuz system, which launches things like the humans to the ISS as well as Progress capsules. And the Progress capsule failed late last year to reach the International Space Station because the third stage of the rocket failed. And earlier in 2016, a Proton rocket also blew up partway through its mission. And this obviously has engendered a lot of concern because these are the same rockets that are used to carry humans into space. And Russia's been undertaking an investigation to see what happened. And what has been uncovered is that the contractors that build the second and third stages for these rockets, which are the parts that have failed in all cases, had taken some high quality metal components and replaced them with basically knockoffs. With components made from much weaker metallic alloys that weren't able to stand up to the rigors of spaceflight. And these parts were failing and they were taking down the rockets with them. And that's caused the head of the Russian director of this rocket program to resign. And there are officials from NASA in Moscow this week meeting with Russia to sort of oversee what's happening with this investigation and what the plans are to.
This is a terrible time to have this series of problems for, I mean, not only the Russians, obviously, who are pretty much the only group capable of servicing the International Space Station and really just getting human beings into space. I mean, the Chinese are working out the details, but the Russians up to this point have mastered getting humans into space. And right now the Americans, who had also essentially mastered it, now have no way to get anyone into space, and now maybe the Russians can't be depended on to get humans safely into space. For the first time in 60, I'm trying to think, how many years has it been? 40 years? For the first time, we don't have really a dependable way to get human beings into space. It's scary.
Right, that underscores exactly the reasons that NASA is looking to bring in multiple domestic launch partners, because the official NASA rockets aren't capable of launching humans into space. The only people with a currently active rocket capable of carrying people to space are the Chinese. NASA is forbidden by law to work with the Chinese. And the Russian space program has suffered in the last decades. They've had a number of high-profile failures of science missions, as well as satellites and things like that. We should say that the human-certified Soyuz rocket is the safest spacecraft in history. It has flown for more than 50 years now without any accidents. And certainly we expect them to take all prudent precautions with this, but it is an uncertain time for the human spaceflight business. And the next Soyuz rocket carrying supplies to the International Space Station now isn't expected to arrive until March. And I'm sure they'll be watching that launch very closely to try to understand if they've corrected the problems before putting any more humans on top of one of those rockets.
Scary times. It's unexpected that we would go into this place of not being able to dependably send humans up into space, especially with there being people up on the space station, crews waiting in the wings to go up there, the International Space Station requiring, people to boost up the the space station needs to be boosted to maintain its altitude. Like, we're not like in between major programs. There is ongoing habitation of the International Space Station for more than a decade now. What are we at?
That's been the entirety of the 21st century.
Yeah, there's been, since 2001, I think there's been humans on the space station the entire time. So they would be terrible if we stopped having that ability to do that. So either, I guess, but this landscape can change fairly rapidly, right? What, if things go well, what can we expect to see in the next couple of years?
Right. Well, the hope was that, so the original hope was that in 2017, Boeing and SpaceX would be able to launch humans into outer space. And last week, I told you that now the plan is for the middle of 2018 for those capabilities to come online. But there's been persistent rumors this week in Washington that those programs are both behind schedule, and it could now be until 2019. That either SpaceX or Boeing is going to be ready to service the space station with crewed flights.
Wow. And I wonder what would happen if it does push in 2019. Did you see the Boeing did this great live stream video, I think it was yesterday, where they showed off the new instruments of their new capsule. They showed off what the new spacesuits are going to look like. So they've showed off sort of their progress and what's coming next. And of course, we hear from Elon Musk all the great stuff that's happening there, although we always sort of consider ourselves to be living in Musk time. So yeah, I know that wasn't a question, but
it should be pointed out that there are spacecraft docked at the space station right now that would enable the return of all the astronauts on board the ISS. So this isn't putting any humans in danger. And if, for example, even supplies weren't able to be delivered anytime soon, they could always just pack up the space station, leave it in standby, and return home. And the Soyuz spacecraft itself that transports the astronauts back and forth has a nearly flawless safety record, and there's no questions as to the safety and efficiency of the spacecraft themselves. It's the rocket that it carries the Soyuz that's under concern right now.
All right. We've got time for like one more quick story from Kimberly. You want to talk about a new test for life on other planets?
Yeah, so engineers, actually completely unrelated to anything astronomy or astrobiology or physics, have been working with a technique that they think will be very useful for future landers, things like Curiosity and the probes and landers that will land on Enceladus and Europa in the future, a way to detect signatures of life in water solutions down to very, very low concentrations. And it's an application of a technique that's been used in different engineering fields, electrical and chemical engineering in particular, and they're just newly applying it to the problem of astrobiology. This process is called capillary electrophoresis. And what you do, it's a cool thing. Actually, you take whatever your liquid sample is. So say, for example, you have a sample from the underground oceans of Europa. You dissolve this liquid sample in a solvent, which breaks apart the different molecules that are in this sample that you have. You apply an electric field, and based on whatever molecule it is, the sample actually splits apart into its component molecules, things like amino acids or salts or whatever other organic compounds you have. And the electric field naturally splits them apart into their component molecules. And it can work at incredibly low concentrations, and it can also separate out things like amino acids that come from organic versus inorganic processes, which is super cool.
Right. So the point being that in very small concentrations, in very dilute concentrations, you can detect the the elements of the life, the constituents
Right.
of what they're made of and what they're creating in the water. So get one of these probes
Get
down
one of these
into
things.
Enceladus or Europa, and
They predict that when it's on a probe or a lander, it will have 10,000 times more sensitivity than the instruments that are currently on Curiosity.
oh, that's a great idea.
That'll
And
be a
that's
super cool thing for the future.
all right, and you get to go first because we've run out of time to the end of the show.
Okay.
So because I know Paul's got to go in about 1 minute, so I'm going to let you go first. Kimberly, where do people find out more?
Again, people can find out more by following me on Twitter at AstroKimCartier, at my website and blog, KimberlyCartier.org.
Thank you so much for being both our panelist and our special guest this week. It was very cool to hear behind the science. And I bet people would like to do the same thing. We could do that with Morgan and we could do that with Paul, because both
Totally
of you,
do that with Morgan.
we should, absolutely, and Paul.
People want to know what Paul did for his dissertation.
Oh, you want to go down that road?
People were asking in the chat.
Oh,
what
they
did you
were?
do? Yeah, they said, what did Dr. Seaver do?
I did magnetized outflows from active galactic nuclei. Yes, it's all numerical. It's all simulations. All we did was, pretty pictures and movies and stuff.
Yeah. Paul, where do we find out more?
You can follow me on Twitter and Facebook at Paul Matt Sutter. My website is pmsutter.com. My podcast is askaspaceman.com, and you can help support everything I'm doing, which kind of also supports stuff that Fraser is doing indirectly by contributing to patreon.com/pmsutter.
And maybe what we can do as well is we could have me be the guest and you guys can interview me. We'll do that some week.
Ooh.
That'll be fun.
Monkeys run the zoo.
Yeah, exactly. Morgan, where do people find out more?
Yeah, you can check out my latest episode for SciShow Space over at their YouTube channel. I talk about why is the sky dark? Those simple questions that have surprising answers. Otherwise, you can follow me on Twitter at Morgan Renberg or visit my website, morganrenberg.com.
All right, once again, I'm Fraser Cain, publisher of Universe Today. Thanks to everybody for joining us to watch this live. Thanks to our special guests and our special guest, who is also our panelist. It's very confusing. But we don't have an astronomy cast after this because we already did it because Pamela was traveling. So your afternoon is now free. You use it however you want. If you haven't already, make sure you subscribe to this channel. Click the notification bell if you want to know when we're doing these shows live. New episode of The Guide to Space is coming out within a couple of hours, so get ready for it. All right. Thanks, everyone.
See ya.
Hold on. Let me go to the full group.
Oh,
There we all. Oh, wait. There we go. There we go. Everyone's saying goodbye. All right.
Bye.
Thank you so much.